So time to look at model agnostic AI. We've got a couple more sections, a couple more slides here, and then we'll take a slightly longer break of about 15 minutes. So we've started to dip our toes in the model agnostic methods, these ones that don't require you to have a particular model in mind when you're using it. Permutation feature importance is one of the nice global model agnostic methods. The other ones we want to talk about today are partial dependence plots, individual conditional expectation plots, and SHAP. So PDP, ICE, and SHAP. I'm afraid today is a day of far too many my brain's saying algorithms. It's not algorithms. Acronyms. Thank you, Dan. Save me there. It's acronym day in HSMA today. So PDP and ICE plots. What these plots do are drill down to individual features. And they tell us, on average, does one particular feature affect the model's predictions? If we keep all of the other features the same, how does the predicted outcome change? Now, what it's useful for seeing is if there's a relationship. So actually, does changing this feature change the outcome in some way? And what does this feature look like? Is it linear? Is it non-linear? You know, this here we've got age kind of seems to, as you get older, we get this change. The y-axis indicates the model's performance or the model's prediction as the variable of interest is varied. Across the bottom of the plot, we've got these black vertical lines, which are indicating deciles. So here in the Titanic data set, not many of our individuals were below the age of about 18, about 10% of individuals below the age of 18, about 10% between the age of 18 roughly and 20, another 10% between the age of 20 and 22, for example. And then we had about 10% above the age of about 50 in this section. So that just starts to give you a bit of an idea of where is your data clustered. It's just a nice little addition to these plots. Now, the partial dependence plots, again, we import these from sklearn. We import the partial dependence display from sklearn. I'm sorry, I forgot to put that on that slide. I will add that in just a moment. But what we have here is we create an empty plot. Nice thing about this PLT subplots from matplotlib is it allows us to specify the plot size. That's why we sometimes do this. We're not creating multiple plots, but we're just creating a single plot that we can say, please make this plot this tall and this wide. What we're then doing is creating a partial dependence display plot from the estimator. We pass in the model, we pass in our training data, we pass in the feature of interest, we pass this in as a list containing a string with the column name of interest. We pass it, we can ignore the, you don't have to pass in the target because it will actually ignore this to some extent. I meant to take that out, but the target is effectively the class of interest, so survived or not survived, but that doesn't actually get included in here. I'll add in some explanation of that in a moment. Kind average, you'll see why we have to specify the kind in a moment, because what this is telling us is across all of our hundreds of people that we've trained on, what's the average impact of the age on the output of the model. So as you get older, you're less likely, less likely to survive. Now, what will probably make the PDPs make more sense is if we look at what they're built from, which is the ICE plot. Now, a PDP is like an ICE plot is like a PDP, a partial dependence plot, but for each individual data point. So each line here represents a single row of data, a single individual. So let's just consider this for one individual. So we've got all these lines and each one of these is looking at an individual as we change the age and don't change anything else about their data. So let's just consider this for one individual. We've slimmed this down in this case to just contain a few lines. I've highlighted the one we're going to look at. Remember, each one of these is one person in our training data set. We're just going to look at this one. So let's imagine their real data looks like this. Their age is 37. They paid $14 for their fare. They're in class 2. They're male, and their SIB SP is 1. Now, as we change these values, let's change their age to 18. That's not their real age. But what does the model do now if we try and predict their output for their age of 18? Well, what it does in this case is it changes their likelihood of survival. It decreases it from if they were very young. If we put them as a bit older, again, the survival of this individual decreases further. So the partial dependence is giving us, in this case, an idea of their chance of survival. So as we've increased their age, we can follow along their little wiggly line, and actually their chance of survival is down about here. Increase their age further, and we can see that their line is still kind of sitting roughly the same. It's a little bit wiggly along the way, but we can sort of get a general sense of the impact of changing their age. Now, we've done this for every single person in the data set, and we can start to see the shape of the impact of the feature. Does changing the age result in a linear decline? Does it result in more change for some people than others? Do these plots generally follow the same pattern? Do they kind of go in the same direction? Does that mean that we might have some other groups hidden in our data? So let's go back to these partial dependence plots. So what we're seeing here is the average of all of these plots. We've taken the average chance of survival, looking at everyone here, and we've plotted it as this point. Then we've looked at the average chance of survival when we go to, say, age 40, and plotted it as this point. You can see these are on a slightly different scale because of the way that these come through. So the only thing that changes about the code is that the PD plot is the line kind individual instead of kind average. Everything else about this bit of code is the same. If you've got too many values, so you can see it gets a little bit hard to understand what's going on when we've got loads of lines overlaid, we can just plot a sample of features using the subsample option. And we can get the best of both worlds by passing in kind equals both. So we get the orange dotted line showing the average impact, and then we can see the individual impacts, each individual in our testing data set, what's the impact of permuting this feature of age, for example. And this really helps it to tie it together. The ice is effectively what's going on behind the scenes, each one of these individual blue lines showing the impact of survival, in this case, as we change the age. And then the orange dotted line is showing the average impact of this feature across all of these people. Roughly, how does the survival change as we change the age? Does it have much impact? We can also start to split out our plots by different groups as well. There's an example of this in one of the teaching notebooks. But for example, here we've coloured females as purple and males as red, and we can see that age seems to have a more dramatic effect for male passengers than it did for female passengers. Changing age for most female passengers was led to fairly stable. For a certain subset of female passengers, it did seem like changing the age had a more dramatic impact, but it did for most men. You can see that most of the men had a lower chance of survival, so we can start to really tease apart the impact of a feature on different groups. And that's just the code for that plot there. I won't go through it in detail. So criticisms of these kinds of plots: correlated features can lead to really misleading plots. Again, they can sometimes start to hide the interactions between features, and it can be computationally expensive. There's a 2D variant of these plots I haven't shown here, but there's some bonus slides about those. They can really start to take a long time to create because, again, they have to go through and permute all of the different variations of the feature.